Welcome to this lecture on Introduction to Step Response in Engineering Systems. Just a couple prerequisites for this lecture. You should be familiar with the calculus of integration and differentiation and solving simple differential equations. The topic of this lecture is step response. Step response is defined as the response of a system to a step input. What is a step input? A step input, let's call it ut, is an input which is 0 for a certain time, and then it changes its value abruptly to a constant value of s, let's say. Then this input is a step input because it takes a step abruptly and changes its value from 0 to s. If s equals to 1, then we call this a unit step input. So the response of this system to ut, let's call it yt, will be called the step response. And if we want to plot that yt with time, it can be anything. It would be dependent on the system, obviously, and this response is the step response. Now, the natural question to ask here is, why do we want to study this very particular kind of input or response of systems to that input? Well, there are many use cases of step inputs, as demonstrated on the right-hand side with these examples. So for example, if you have a drone or an aircraft for which you want to control the altitude, and it may be at a particular altitude already, and so if you want to change that altitude from, let's say, 100 meter to a 200 meter, that is a step input. And so you may want to study how your system responds when you introduce that step input. Similarly, you can imagine a fan, you switching on or off a fan are all step inputs. Similarly, a biological or chemical reactor. Whenever you introduce change into a system, that is a step input. And so it's very important to study the response or to study how we can model the behavior of the system to this very common type of input. A second kind of use case is to also desire something from the designer by describing how you would want your system's step response to look like. So for example, for this drone example, I can ask the aircraft or the drone designer to give me a drone that responds very fast to my step input. So I want to reach my desired level as quickly as possible, something like that. So those are specifications that I can ask for the designer, and those could be expressed in the step response. So it is important to study the math behind how we can compute these step responses or how we can analyze the step response of various systems. So to take a step towards that, let's take a simple example. This example will be a differential equation, first order differential equation, dx by dt equals minus ax plus u of t. So now here u of t is the same step input, and a, I'm assuming, is positive, and let's assume also that it is at rest, so x of 0 is 0. It's the initial condition 0. Now we can integrate this differential equation to get the solution of the differential equation, which would express xt as 1 over a 1 minus e to the power of minus at under these assumptions. And u of t equals to 1. So this is what would be called the step response for this very simple example. So you may be wondering how I came about this equation. And that is simply by solving this differential equation. And you may also solve that differential equation. I have solved it on the right-hand side here, but have not gone into the details of step-by-step solution. So if our system is modeled by this differential equation, and if this is its step response, we can take a look at how it might look on a 2D plane. And we can plot x of t with time. And since this is negative exponential, a is positive, what we would get is that this would asymptotically reach this value of 1 over a, and this would be our step response for this system. Now, There are various interesting properties of the step response that are useful. As I said earlier, we want to use the step response as our specification for various systems or as a metric of how the system is performing. So system performance and system specification can be expressed as step responses. So let's take a look at how we can do that with computational examples so that we don't have to integrate the equations by hand, even for complicated examples, and we can just take a look at how to assess a step response. So this is the first computational example of the same differential equation that we just looked at above, but now we can use Python tools to solve the differential equation so that we don't have to worry about solving it by hand. So here I've written down that differential equation and then solving that using Python ODE and function. And it leads us to the step response, which is shown on the plot on the right-hand side. And this plot is very much characteristic of first order response of a system where you see this asymptotic growth towards a steady state. The second example is the more interesting one, is of the second order differential equation. The differential equation is written out here in this Python function. It's basically the same differential equation that we write for a spring mass damper system, which I have not gone into in this video, but it looks something like this. If this is my system model where I have a second order differential equation and the step input on the right-hand side, then I can solve this differential equation by writing down this Python function as shown here, and then solving the differential equation with ODE and just like above. So as I mentioned already, we want to use the step response to characterize the performance of a system or to write the specification of what we desire out of a system using the step response. So how we may do that? Let's go back to the motivational examples that we discussed at the beginning of the lecture. And let's take altitude control, for example. We are at a certain height already, and we want to introduce a step input to that system to take it to a next altitude, let's say from 100 meter to a 200 meter. Now, what might be a property that would be desired for the aircraft once we introduce this input? Something that comes up the top of my head is that it should be a fast response. And the metric that measures that would be called the rise time. So rise time can be defined in many different ways. One way to define it could be the time that it takes to go from, let's say, the 10%, so that is the 0.1, 10% of the step value. So once it starts to grow or to increase its response, how much time does it take to get as close as possible to the step value, the desired value? So we may say something like the time it takes to go from 10% to 90% of the step value. So that would be something like 0.9 here. And what we would get is a vertical line here, a vertical line here, and then this time would be called the rise time. So you can see that it takes around 2.5 units of time of rise time. And a better rise time might be something like this. So we may desire this kind of response, which reaches the desired level much faster. But there are trade-offs to this because what may happen is that this may overshoot because it's going that fast to that desired level. It may overshoot and be something like that. And so that's the next metric, overshoot. So for the blue curve, you see that the overshoot is less than the black one. And we can define overshoot in a way that maximum of the response minus the desired level that we wanted to reach divided by the desired level. And we can convert this to percentage if needed. So that's the second metric. We would ideally want our system to not overshoot much because we want it to be as close as possible to the desired level. The third and important metric is steady state error. So first of all, if we are introducing a steady state, a step input, we want the system to reach the steady state. And what do I mean by steady state? the state at which it stops changing mathematically, state the time at which dx over dt is 0. So an equivalent of that would be to look at what the steady state error is in the step response. So we want it to reach the value 1, but it may reach some other value at steady state. 1 YSS is the steady state value. And this would give us a measure of the steady state error. So we would want this error to be as low as possible. So with those metrics, we can characterize the performance of system by using the step response, and then describe how we want our system's response to be so that we can optimize it. So with that, I'll conclude this lecture. Thank you.